So in this video, we'll learn about the concept of addressability. There are broadly two types of addressability. One is called byte addressability and word addressability. I'll explain what these are with a simple example. But before we go there, let's understand what is an address space. This is also sometimes referred to as the physical address space, right? Again, this is a concept that you will also learn in operating systems, right? So there is a lot of concepts that you learn in computer organization and architecture, which you'll also learn in other subjects like operating systems, because an operating system is built on the physical hardware itself, right? So a physical address space is basically all the addresses that you can have. For example, imagine a memory. Imagine a main memory which has 2 power n cells, right? Imagine it has 2 power n cells. If it has 2 power n cells or words, right? Remember, each of this is a cell, right? And let's assume the cells of the addresses are 0 to n minus 1, right? So this is 0 to n minus 1, right? And here I've also, the address is an n-bit address, and here your capital N, log of capital N base 2 is small n, right? Very simple concept here, right? Suppose, imagine your address space is, suppose you have a memory which has 2 power n cells. Then how many addresses can you have? You can have addresses from 0 to 2 power n minus 1. These are all the addresses that you can send to the memory chip itself, right? So this is what is called as address space. Address space is the set of all the addresses that you can have for a given physical memory chip, right? So this is one concept. The next concept is called as byte addressability. Very simple concept actually. So byte addressability means, okay, let's take this example, right? Again, these two, I'll try to compare these two so that you understand this concept better. There is byte addressability and word addressability. Imagine if I have a memory chip with 0 to n minus 1 cells or locations, and of course n equals to log, so log n base 2 is lowercase n. This small n or lowercase n is the number of bits in the address, right? So now imagine if I send an address, an n-bit address. What do I get? Whatever is the width of this word. This is called the word width or the cell width, right? So imagine this is 8 bits. Imagine this is 8 bits wide. Then this is my data bus. This is my data bus here, right? This is my data bus here. My data bus my k in the data bus equals to 8, which means now using a single address, look at this, using a single address in the address space, I can address one byte. I can address one byte using one address. Using one address if your memory is n cells cross 8 bits per cell. Look at this. If your memory itself is n cross 8, what is this n? N is the number of cells, 8 is the number of bits in each cell, right? If this is the case, very simple. I can address every byte. Remember, a byte is a fixed unit. A byte is 8 bits, right? Similarly, there are also some other terminology. There is also this terminology called as nibble. Nibble means 4 bits, right? So a byte is a fixed number of bits. On the other hand, the word is not a fixed number of bits. Okay. For example, this memory has a word size of 8 bits. But imagine a world where if this is, look at this, if k equals to 16, imagine a world where k equals to 16 bits, then what happens? One word can be equal to 1 byte. Again, this is 1 byte if your memory chip is n cross 8 chip. If your memory chip is n cross 8 chip, your one word is 1 byte. Your one word could be 2 bytes if your memory chip is n cross 16. Right? Your one word could be 3 bytes if your memory chip is n cross 24. So the definition of a word is not fixed. The definition of what a word is nothing but a cell, right? The definition of what one word corresponds to depends on the number of bits per cell or per word, right? So word addressable, imagine a world where you have 16-bit cells. Okay, each cell can hold 16 bits. Now, can you address exactly 1 byte? No, because if I give an address, look at this. In this case, imagine this is 16 bits. Okay, let's take this example, right? Let's take this example. In here, if I give one address, here one address corresponds to here one address corresponds to 2 bytes, not 1 byte. So in this instance, when each cell or word consists of more than 1 byte, what we have is a word addressable memory, right? What we have is a word addressable memory, right? But now your question again, by default, every microprocessor we say, or every microprocessor, and at the end of the day, your RAM or main memory doesn't exist in isolation. It always works with respect to along with a CPU. Remember that it's your CPU that is sending these addresses, and this data is actually going back to the CPU, right? So at the end of the day, your memory works in tandem or in collaboration with the CPU, right? So by default, we always assume that our in a standard microprocessor design, and memory design, right? So to be more specific, in the standard microprocessor design, because your memory may be word addressable. Look at this. This memory, if it has 16 bits, it's word addressable. It's not byte addressable. But all microprocessor design, by default, we assume it to be byte addressable. Because look at this. At the end of the day, again, this is a concept that we learned even in C programming, when we learned C programming, right? When we learned C programming, we said we can obtain 1 byte from memory. We can allocate, let's say, a character. In C programming, we have seen this, right? I can allocate 1 character, whether my CPU could be, see, in this case, let's assume my CPU is a 16-bit CPU, right? Which means the address is going to be 16 bits. And let's assume my memory is also 16-bit address, 16-bit, 16-bit word size, right? Even this CPU with this type of memory, if I write a C program, right? And if I compile the C program for this 16-bit CPU, I can still say char A. This char A, again, depending on the compiler, but in most situations, this will allocate 1 byte. Remember, this will allocate 1 byte. So by default, we assume whenever we write programs or whenever we design microprocessors, we assume everything to be byte addressable by design. Okay. Now the big question here is this. A very important question is, imagine if I have a 16-bit CPU, right? And my memory is also, so there are multiple cases here. Okay. So first case, let's think of first case, right? Imagine I have a 16-bit CPU, and let's assume each of these words is also 16 bits. Now, if I want to address only 1 byte, then if you think about this each cell can be thought of as 2 bytes. Look at this, each word or cell can be thought of as 2 bytes. This is 1 byte, this is other byte. So if I exactly want this byte now, what do? I tell the CPU to fetch this whole data that is there in address location 2. I'll ignore this first byte or this first 8 bits. I'll only use the second 8 bits. This is simple. Look at this. If I want a byte addressable, imagine you're writing a C program and you wrote char A. Let's assume char requires 1 byte. Okay, but your architecture is like this. Let's assume you have a 16-bit processor and your word width or your memory itself is, let's say, some n cross 16 memory. Still, I can get it to work very easily. How do I get this to work? Very simple. If I want to load whatever data is there in this memory, I'll give this whole address, this address 2, okay, and I'll copy this whole. Look at this. I'll fetch this whole word. Of this whole word, I'll simply ignore this. I'll only use the last 7 bits or the second byte here, right? So you can actually have byte addressability even when your CPU is not 8-bit CPU, even when it is 16-bit CPU. Even when your memory word width itself is more than 8 bits. You can still get it. There is one more very interesting case. Imagine a case like this. Imagine that I have a 16-bit processor. This is an interesting case. Okay. So imagine I have a 16-bit processor. I'll actually show you a simple example. Okay. I have a 16-bit processor, but my memory is n cross 8 bit. Look at this. My memory, the width of this memory is 8 bit. Okay. Now, what does a 16-bit processor want? The 16-bit processor would want to fetch 16-bit words in one. So for example, let's look at this. Okay. This is how a machine instruction looks like. Look at this. When you write your C programs, right? So when you write your C program, you could write something like, you could say, okay, A equals to X. So suppose if you did this, let's assume you have some data stored in X that you want to copy it to another location called A. Okay, or maybe you want to perform this. Suppose, let me give an example. Suppose you have a variable X, you want to make X equals to X plus 1. Okay, this is your C program, right? The way it gets converted to machine level language is as follows. To perform this operation, again, very, very importantly, one more very important aspect about a processor is this. Okay, I'll explain this so that you understand this machine level instruction, and then we can move forward from there. Okay, suppose I have this. Let's assume this X is stored in memory location 2000. Okay, so let's assume X is 1 byte. Let's assume this is my memory. Okay, let's just assume this is my memory. Okay, so let's assume X is 2 bytes, just for simplicity. Okay, so let's assume X is 2 bytes. Let's assume X is an integer which requires 2 bytes. Let's just say. Okay, now what do I want? I have a 16-bit processor, right? So when I have a 16-bit processor with an n cross 8 memory, so this will get translated into this. To perform this, what happens here is, let's assume the address of X. Okay, because this is 8-bit, right? Because in each memory cell I can only store 8 bits. So let's assume this 2 bytes is byte number 2000 and byte number 2001. Let's assume in these two locations, because this is 1 byte, right? In 2000 I can store 1 byte, in 2001 I can store 1 byte. Okay, look at this. What I've written here is basically, I've written 2 numbers. This is actually 8 bits. But instead of writing it in bits because it's very long, I wrote it in hexadecimal. 1 byte, look at this. If I have a number like this, 1 byte translates to 2 hexadecimal. This is 1 hexadecimal number. This is 1 hexadecimal number, right? So this is base 2. This will be base 16. Right? Very simple concept here. So for example, look at this. So let's assume some value is there in my X right now. Let's assume the value in X, because X requires 2 bytes. The first byte is, let's say, byte 2000, or the data stored in cell or address 2000, and the data stored in cell 2001. So these two together, I can write them as 1223 base 16. Look at this. Look at what I've done here. Whatever is there in the lower address, I've placed them in the lower bits. Whatever is there in the higher address, whatever is there in the larger address, I've placed them in the larger bits. And remember that this number is not decimal. This is base 16. This is one way of, because it says my data is in 2 bytes. My X requires 2 bytes. The first, again, the 2 bytes are 2000 and 2001. One way of interpreting this data is to copy 23 into the lower bits, 12 into the higher bits. This is one way of doing it. There is another way of doing it. Okay, we'll discuss them in lots of detail. One is called the little endian, other is called the big endian. Okay, we'll come to that. The other way of doing it is, I can take the 23 as my higher bits. I can take my 12 as my lower bits. This is another one. This is the more popularly used approach than this, right? So again, we will come to this. There are 2 ways of interpreting these addresses. One is called the little endian, other is called the big endian. I'll explain that in a little while. But there are 2 ways of interpreting it. In one way, the 23 here is placed in the lower bits. Here the 23 is placed in the higher bits. This is less often used. This is more often used. Given this, now let's understand how everything works. How this whole line of C program gets translated to machine instructions, and how the whole thing is executed. So in this example, we'll stick to this notation. Okay, because this is more popular, more widely used. So we'll interpret this 23 hexadecimal in 2000, 12 hexadecimal in address 2001. Both of them hexadecimal, will interpret as 1223. So if this is the data, when I increment it by 1, what should it become? It should become 1224. It should become 1224 base 16. Right? So don't worry about little endian, big endian. They're new terms to you. I'll explain them in lots of detail just in a few minutes. So this whole thing gets translated into a bunch of instructions or machine level code. Okay. So this, what we've written in C, the compiler takes this and compiler converts this into machine level language. The machine level language itself consists of instructions like this. So first what we do now is, whatever is the data that is there in X. Let's assume the address of X is 2000, 2001. We only give one address, 2000. So whatever is stored, again, because remember it's a 16-bit processor, where whatever it fetches from memory, it will fetch 2 bytes. It will never fetch only 1 byte. It will fetch 2 bytes. Okay. So it could fetch byte 2000 and 2001. So move whatever data is here into a register. R1 is a register. Now you might wonder, what is a register? Okay, let's understand that, right? Very simple concept. You have your CPU here. This is your CPU. Your CPU has a processor, has a basically processing engine, but it also has something called as registers. Again, if you recall, registers is a concept that we learned in C programming language also. When we learned C programming language, C has a keyword called as register. So registers are basically, okay, so let me, instead of drawing it like this, registers are basically memory within the CPU. So you could have register A, R1. There are special purpose registers called like an accumulator, like a program counter. We'll understand all of this in a little while. Okay. So there are a lot of registers. This is memory. Again, there is very little memory here. Your RAM, you could have on your RAM. Look at this. Your CPU talks to your RAM, right? Your RAM could be a few GB of RAM, but your registers will be just a few kilobytes of RAM, register space. Registers is memory space that is there within your CPU that the CPU itself can access very, very fast. So the CPU can access data which is there in the registers much, much faster than it can access data in the RAM itself. So this is your, let's say, RAM, right? So what this does, and CPU can perform operations on data that is there in the registers very, very fast. So what this does is it copies, look at this, it says copy whatever data is there in address 2000 to register R1. Let's say register R1 is a register in my CPU. Now because we have a 16-bit processor, it doesn't just copy 1 byte, it copies 2 bytes. Okay, so again, your register is also going to be 16-bit. Your register R1 is also going to be a 16-bit register, because what we have here is a 16-bit processor. So what it does here is, again, there are 2 possibilities. We'll come to those 2 possibilities in a little while. One possibility, one very simple possibility here is, so since we have a 16-bit register here, whatever is there in address 2000, we copy it to the lower bits here. The lower 8 bits. Look at this. This is hexadecimal. Remember, this is hexadecimal. So 2 digits in hexadecimal become 8 bits, right? So this 23 is stored in these 8 bits. So whatever is there in address 2000 or the lower address is stored in the lower bits. The higher number, the higher numbered byte, this 12 gets stored here. Okay, so this is one possibility. This possibility is called as the little endian system. So this possibility, let me write this down here, right? So this possibility is called the little endian system. So what is a little endian system? Look at this. Here I have 16 bits that I need to fill. Here I have 16 bits that I have to fill. So first, what am I doing? I'm copying. So the address that I've given, again, remember, this is a byte addressable memory. But what I have is a 16-bit processor. So I gave it address 2000. So what does it do? It knows that my register 1 is 16 bits, which means I need 2 bytes or I need data from 2 addresses. So whichever is the lower address or lower numbered address, it copies this into the lower bits. Whichever is the higher number address, this value gets copied into the higher valued bits. Right? So this is also base 16, obviously. This is called the little endian system. This is the most widely used system by microprocessors. There is also something called as a big endian system, which is not very popular, right? The big endian system basically says, instead of ordering it like this, it does the exact opposite. So the big endian system, what it does is this. The big endian system basically copies whatever is there in the lower address in the higher bits. So it copies 23 here and it copies 12 here. Right? Again, these are hexadecimal numbers. That's why I'm writing base 16 here to be clear. Right? So this is called as a big endian system. In the big endian system, whatever is there in the lower numbered address 2000 is copied into the higher numbered bits. This is the higher numbered bits, right? Whatever is there the higher numbered address is copied into the lower numbered bits. But big endian is not very popular. It's the little endian which is always popular. So I'll continue to use the little endian because, again, by default, you can assume that processors always use little endian unless otherwise stated. right? So what you have here is you have 12 and 23. Both these numbers are in base 16. Okay, now what happened here? Whatever is the 16-bit number which is there in addresses 2000 and 2001 got copied to my register R1. Now you might say, how does a microprocessor understand this? Again, this type of writing your program or converting your program from this high level language like C program to this type, this is called assembly level language. This is called assembly level language, right? This is more human readable because it has commands like move. So your assembly level language gets converted to machine level language, which only contains bits. So there is actually a code corresponding to MOV for every processor, for every instruction or for every command like this, right? So there is a fixed bit sequence. So in your microprocessor, the machine level language might say move is equal to 1011 101010. This is move. R1 also will have some specific bit sequence. Okay, 2000 also, you can write 2000 into a bit sequence. So what happens is, again, but we will focus on the assembly level language because we can read this. If I start writing these commands or these machine level instructions in bit sequences, we'll not be able to read what's happening also. So for most of computer organization and architecture, we will stick to assembly level language, which is more human readable, but translating from assembly level language to machine level language is simple. Because there will be a code for MOV, you just copy that code. There will be a code for register 1, write that. Your 2000 address number itself, right? So 2000 gets converted into binary and the 2000 address is written here. It's very simple. Assembly level language to machine level language translation is very simple. It's all about translating these keywords to a sequence, to a bit sequence or a bit string. Okay, so we will focus mostly on the assembly level language itself through the rest of this course. Okay, so the way this would work out is, first we move whatever. So by the end of this instruction, what happens? Whatever is there in address 2000, 2001 is stored in register R1, right? Then you will have a command like this, increment R1. So what does this instruction do? This is a assembly level instruction. What it does is, whatever data is there in R1, increment it. INCR R1. Okay. So this single line is translated into multiple machine level instructions. Again, this is a concept that you will revisit in compiler design. This is the same concept that we will also revisit in operating systems. This is very, very important concept. That's why I'm going so slow here, right? Similarly, your x equals to x plus 1. Now we have not yet done it, right? So now R1 consists of whatever value was there. Look at this. Your value in R1 was 1223. We incremented it. So this becomes 1224 now. Now what we do now is we say move to 2000 from R1. Now what happens? Look at this. Whatever data is stored in R1 is now written back to the address. Again, R1 consists of 16 bits now. R1 consists of 16 bits, right? The upper 8, the larger 8 bits, right? These higher number bits will go to address 2001. These lower number ones will go to address 2000. So this will become 2004. Look at this. What did we do? First, we moved whatever data is there from address 2000 and 2001 to R1. We incremented R1, and whatever is there in R1, we copied it back to 2000. Okay. Very simple. Very, very simple concept. Sometimes this command may not be move. Sometimes you may have a command like CPY, which means copy. Okay. So sometimes, again, this depends on the microprocessor. Every microprocessor has a different instruction set. This is called the instruction set. If you go and open any microprocessor textbook or any microprocessor data sheet, you will encounter different instructions for every microprocessor, right? I hope you understood this concept, right? How this single line in C program gets compiled, translated to this, and how this thing works on the 16-bit C, on a 16-bit processor, right? Now, again, this all boils down to your addressability, because what do we have now? Very importantly, we have a 16-bit processor. But we have an 8-bit addressable memory. But still we can make this whole thing work by using a scheme like the little endian method. Right? Very, very, very ingenious concept. Very, very beautiful and elegant actually. Right? Very simple concept, but very, very important to grasp this. Again, you have to always realize that anything that you write in, again, computer organization connects a lot of subjects. Again, and it's also a core subject to understand many other things. You have to understand, again, whatever you learned in C programming will make far more sense now. Again, to learn compiler design, to learn operating systems, all these subjects, having a good understanding of computer organization is mandatory, right? Because you have to understand how the actual computer itself works to be able to write good code, to be able to design a compiler, or to be able to build an operating system, right? Very simple concept here. Now coming back to this, again, this is the logical view. There is one more thing that I wanted to bring to your notice. This is the logical view, right? This is the logical view of your memory. And this is the physical chip itself. This is the physical chip itself, right? So this chip is 64K cross 8. So one example like this chip is your 64K cross 8, where you have 16 address lines, you have a read-write pin, and you have a data pin of 8 bits. Remember, this is the logical view. I'm always making this very clear. This is easier to think about what's happening. This is the physical chip itself. This is how the chip looks like. The internals are not clearly understood. Whenever we are looking at the physical chip itself, we only care about the pins, the inputs and outputs. When we are looking at the logical view, we understand how the data is actually internally stored. Okay, that differentiation is very, very important to grasp this concept.